It's very, very difficult when you explore the unknown to exclude all the mistakes. That's why sometimes there are people that produce something. They are really convinced they did all what they could, and actually they were a little bit optimistic or missing a point somewhere else. So it's it's part of the game, but the failure is the most important element that any scientist, any PhD student has to learn. Failure is the most common part of the business. If you don't know how to fail, change job, because you will not survive, failing so often.
Welcome to People Doing Physics, the podcast that explores the personal side of physics from the Cavendish Laboratory at the University of Cambridge. I'm your host, Jacob Butler, the Outreach Manager here at the Cavendish. Today we have the privilege of being joined by one half of the team behind what is arguably one of humankind's epochal breakthroughs, the first observation of a planet outside our solar system. Both a professor at the University of Zurich and Jacksonian Professor of Natural Philosophy here at Cambridge, Didier Queloz began his research career by achieving the great aim of all PhD students, a publication in Nature. Since then, the techniques and instruments he'd pioneered have led to the identification of over 4,000 other exoplanets and revolutionised our understanding of planetary formation. His more recent work looks at the detection of Earth-like planets, understanding their habitability, and the search for universal life more widely. He is now director of the Leverhulme Centre for Life in the Universe here at Cambridge, an interdisciplinary hub looking at how life emerges, evolves and persists in the cosmos. In the course of his career, he has published hundreds of papers and been recipient of numerous prestigious awards, including the unarguably most famous of all scientific awards, the Nobel Prize, which he shared with Michael Mayer and James Peebles in 2019 for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. In this episode, we'll talk about his route into physics, his work looking at one of the profound questions of whether humankind is alone in the universe, and whether he replaced the bike that made him miss the call from the Nobel Prize Committee. So, Didier, thank you very much for meeting with us today. It's great to have you with us.
It's a pleasure. Thank you.
And I read your Nobel Prize interview where you did mention that you were going to replace that bike. I was wondering if you got around to it.
Yes, I did actually. That's the day I got the announcement. Was just starting with a very bad day because I'm biking like everybody in this university to move around, and my bike had trouble. I had to change the chain, and I was late at a meeting, and I came with my hand all dirty, so it was really a bad start of the day. Well, at 11, everything changed, and it becomes a kind of a crazy day.
Lovely. Well, we'll talk more about that later, but as is tradition on the podcast, we'll start at the beginning. So, was science something you always saw yourself pursuing, or were there other potential routes that you nearly followed?
Well, that's an interesting question. There is certainly a characteristic that was essential, I think, for me deciding to become a scientist and to be a successful scientist is I'm extremely curious, and I've always been extremely curious, and it has never changed, I think, since I was a child. I expect most of the child are curious. I was certainly amongst the most curious of them, but this feeling has never left me, and I think this is probably the reason why I ended up being a scientist, because what is the best than to be a scientist, to make a living of being curious. So that's really what defined me, and that's the reason why I ended up studying physics. I could have studied anything else, I suspect, but the reason why I studied physics is quite funny when I think about that now, is I was just incapable of choosing what to do. I ended up my corresponding A-level in Switzerland called Abitur or Maturität. And then I said, I love so much learning. What can I do at the university that would not be a job? And I thought physics was a great topic, because it leads essentially to nowhere. Being a physicist is not a job, it's a state of mind. You learn how to approach the secrets of nature, essentially, in a very rational way. You build up machine, you work with the mathematics. I was quite easy with mathematics. So that's the reason why I started physics.
So it was that feeling of inevitability that you wanted to be curious, remain curious, and not tied down to a particular career path or.
When you're curious, it's a bit of a random, erratic feeling, and it's kind of a soft disease in a way because you don't know how to organize this. So when you start being a scientist, that's certainly the best way to make sense to this extremely strong urge of curiosity. I suspect for an artist it's a different urge. It's maybe the urge of expressing yourself that is very strong and push somebody to go to art or any kind of art. For a scientist is really what it is. So bringing this kind of structural way, a bit like a painter needs to be, or to know how to paint first before deconstructing, inviting a new way of painting. I think you need to structure the way you approach this curiosity, and that was really physics brought me. I've never been a super gifted student. I was a good student. I was part of the good 10%, but I was never part of 1 or 2%. And it took me time to realize that when I really was into something, when I studied physics, I could be really good. And I really started to be really a good student in a sense, really when I joined the university, because that was exactly matching was my brain, what I really wanted to do, and I really enjoying so much, so I couldn't stop. So I started a PhD essentially right away, because for me that was a perfect way to continue to feed this curiosity.
Was astrophysics always the route you were going to go, or were you sort of looking for lots of different
not
branches?
at all. I think physics is such a great topic, and anything is really interesting. It depends a bit of the what's going on at the time you're a student. In my days, it was the 80s, the pinnacle of physics, the state of the art, the top stuff you could be doing was particle physics. The particle physics has plenty of breakthrough, Nobel Prize discoveries. Being in Geneva, it was easy because I was close to the CERN. In my classroom, I happened to have the daughter of Rubiat, the Nobel Prize winner. So there kind of this excitement about particle physics. So obviously, I studied particle physics. That was one of my topics. But at the same time, I had an eye on astrophysics because to me, that was also great, this beginning of the black hole stuff, and we started to understand the galaxy. There was the big cosmological model start to appear. All this was really, really good and was feeding my curiosity. And it was building equipment. I love building equipment. It was the beginning of computing science. I just love computing science. I just feel very easy with that. So all this was matching, ticking the box. And funny enough, when you are doing your studies, you have to do practicals, and I mean advanced practicals, saying for 3 months you have to do a project. And I picked 2 projects. One, it was an astrophysics project. So I was doing with observations, data analysis. And the other one was a particle physics project. I was to assemble a detector and to do some measurements. I just love both projects. But I realized something. The particle detector, I was sitting in a box, essentially, in the dark room in the basement. While in astrophysics, it was cool because I had to go to telescopes and deal with the data and nighttime or so on. So at some time, I said, well, if I want to do a PhD, a couple of years, do I want to spend my PhD really in a cave, dealing with an equipment in the basement? And at the end, I decided to go for astrophysics for that reason. I was very much into maintaining. I used to be a ski teacher. I love nature. So for me, that was kind of an emotional choice to say, oh, if I have to do something, let's do it in a place when I feel at ease. And that's how I decided for astrophysics. So, sometimes things leads you to somewhere. It's just an emotional choice. It was anyway good physics. The professor were good anyway. Opportunity were good in both ways. So at the end, it was just a matter of one topic be more appealing, corresponding more to my state of mind or my lifestyle.
Indeed. So pursuing your passions and giving you a chance to go abroad to nice places like Hawaii rather than, as you say, sitting 150 metres underground in CERN. So you then went on to do a PhD with Michael Mayer as your supervisor?
Yeah, correct.
Was he somebody you sought out, or was it a sort of serendipitous pairing that the two of you ended up together?
Oh, picking the supervisor, it's a poem. I mean, it's a lot of things that goes with that. I can't say with Michel it was a click. You call it a love affair if you want. I just like the guy. He was a good professor. He's not extravagantly good. He was a good professor. He was a nice guy. He had a working style that fitted my way of working, which means he was not always behind me. Actually, he was not very much behind me, which was perfect because I love being independent. And what he was offering to me was cool. He was developing a new machine. It was new. I had a lot of freedom. I had to go to Haute-Provence. It was nice to go to Haute-Provence back and forth. So it ticking all the box, and he had a job as well. So for me, it was just a good choice, good feeling with him, good project. Let's do it. And it turned out to be a very good choice.
Indeed. So any advice you'd give to undergraduates or looking at sort of PhD supervisors, what to look for in a supervisor?
Well, the advice I always give to any students is you really have to listen to yourself. Don't look at the CV, don't look at the publications. I mean, you have to think that you will have to spend 3 years or 4 years of your life in a most intensive way when you will have to grow up and learn, and it would be a kind of a strong moment of your life. You will always remember your PhD. So better to make it pleasant. So make sure that you have a good connection with your PhD supervisor. Doesn't mean you have to always see him every day. It means you have a good connections, you feel at ease. You also feel the group is good. It means you feel that the other PhD students feel at ease as well. And when I recruit PhD students, my usual advice is I tell them, well, why don't you talk to my team without me being around? And they will tell you what they want to tell you. I don't want to hear it. You will have a good idea who I am, because what can I say? I mean, I work one way that doesn't fit some students, but that do fit other students. So there is all this that goes around. It's really a matching game here. At the end, the knowledge that the professor has is not really super critical, because if you do that in a good university, the kind of a level is high enough. You will have somebody that knows plenty enough for you, and at the end of your PhD, the topic you will pick will be so much pushed to the extent that you will know more than your professor, which is exactly what has to happen. So now let your heart talking, your feelings, talk to the people working with this professor, and at the end, the choice of the topic is not really super critical, I think.
That's interesting. So your work famously led to the first observation of an exoplanet, and I presume this wasn't just simply a case of looking at the right place through a telescope. So do you want to talk us through how you went about this discovery?
Well, there is a series of elements which is interesting in this story. First, we built a machine which was really new, and that ended up to be better than we thought and was the plan. So in a way, we did a good job. I did a good job. It was completely new at that time. A lot of new components, completely new approach, new data analysis. So we really invented a new ways to approach, which is still being used. It's funny that even the format of the data is still being used today. So we will install a legacy in that sense with this machine. Of course, the machine has been improved. The precision has multiplied by 100, but the same concept, same approach, same way to do that. So we did that very well. That's the first element. The second one is we had the kind of good reading of the situations, because in the 90s, there were no planet. Some team had observed already a very limited number of stars, a Canadian team, about a dozen, and they reported no detection, no discovery. So we were aware that if we have to detect something, we have to observe a significant number of stars. So we took the decision to multiply by 10 essentially the number of stars we would observe, and then to be really systematic in observing as much as we could the stars, and that's how one of the samples was 51 peg. It was just one amongst many. And then because we had a system built into fast response, in the sense that it's not only you collect the data and you sit on your data for months and then you look at it later. The way we build it, and that was one of the ideas of my supervisor, is no, it's better if you have a system that can process the data during the night, or at least shortly after the night. Then the day after, you know what you have done. So it turned out to be tremendously useful, because in the case of 51 peg, very clearly the data didn't match my expectation right away. I thought they were somewhere a mistake, because you expect the speed not to change from one day to another one, except if there is an extreme effect, but you don't expect this to see. But I was seeing a change of the speed. And of course, because I was processing the data in the night, the day after I could re-observe the same stars. And what was really panicking moment is the speed had changed again. So I had a kind of an erratic feeling that these stars had a completely erratic behavior. Every night the speed was different. And I would have never picked that without the whole system. So that was really an element of the fact we've been successful. The second one, which I was a PhD student, very focused, very obsessed. I spent a lot of time on building this machine. I really wanted this to work. So when I saw this, I thought something is wrong. So I spent a lot of time to debug and to work on it to make sure the system was working. And in a way, we got lucky or we did really good work, because most of these new systems that start, they never work the way you want. In our case, they work pretty much the way we wanted. So I mean, all the choice we've made was really right. And I could rapidly find out that there were a systematic pattern behind it. And the fact that I was in PhD, at the end of my PhD time, I was really motivated. So I was on it. But I was also on it with a bit of a feeling that maybe something is wrong here. So I didn't talk to my supervisor right away. I really waited. I have enough data to have a convincing case. So I was really obsessed by that to make sure I beat my case. And then I can proudly show, this is what I found. What do you think? And that's what happened. Of course, Michel was skeptical. He was right. The planet doesn't make any sense. It's a 4 days Jupiter planet. 4 days means it's 20 times closer to the Earth. Well, of course, I showed him all the data, what I did, and at some point he had to admit, yes, that must be right. And then we worked quite hard to find out that it cannot be something else, because the problem is we didn't see the planet. We only saw the change of the speed of the star. Then you have to make sure the star doesn't produce this just for other reasons. So it took us some time. The paper is a beautiful example of let's say, a well-written piece of work with no rush, because we were so unsecure. We were secure of the data, but we were insecure about the reaction of our colleagues. So we worked really hard to come up with this kind of negative proof. So you imagine all what it could be, and you say it cannot be that, it cannot be that, it cannot be that, because. At the end, you say, oh. The only thing that we are thinking right now, among the long list we have excluded, is a planet. We're really sorry. It's crazy, I admit, but that's the only way. And that's really how we run the paper. And you know, it's funny because I had to read the paper at the time of the Nobel Prize, because I forgot at that time what we wrote in the paper. And I said, oh my God, this was really a good paper. So I'm very proud of this paper that we did with Michel, because we really did it the way it had to be. It had to be done. And we did all the job we could do. This is why we came up with the discoveries. And the reason why we went a bit faster than the others, I think, is because of the reason I mentioned. We work a bit better. We had more access to the data. I was a bit more obsessed maybe than the others. And we observed a good star at the right time.
It's fascinating to hear as well that sort of self-skepticism you have to have, that sort of sanity checking just yourself as well. I think there's a lot of misconceptions of science and the idea that you're sort of going out there to break things, whereas actually it's...
you have to realize, this is maybe a notice of cautions. Most of what you do in science is failing. I think success is very rare. So you use that is going to fail somewhere. So what you see is something, you're pretty sure that this is just something wrong. So this is something that is a trademark of a good scientist that survives in the business, because he's used to that. Most of the time, it would be wrong. So it's a more natural thinking when you have something that doesn't look right to find there must be a mistake somewhere. Well, then the good scientists work hard and to find out whether they can explain what is the mistake here. And if they can't explain the mistake, that is become interesting, because then it may become a discovery. But it's very, very difficult when you explore the unknown to exclude all the mistakes. That's why sometimes there are people that produce something, they are really convinced they did all what they could, and actually they were a little bit optimistic or missing a point somewhere else. So it's it's part of the game, but the failure is the most important element that any scientist, any PhD student has to learn. Failure is the most common part of the business. If you don't know how to fail, change job, because you will not survive, failing so often.
Now, of course, later, well, quite a lot later, I think it was nearly 25 years, wasn't it? You won the Nobel Prize for this work. Now, the Nobel Prize, I think, has a tendency to highlight sort of small groups of people, and sort of often plays into that idea that science is progressed by sort of individuals doing magnificent things. And not to say, of course, that you weren't doing magnificent things, but I was wondering, as someone who was inside this, did it feel like you were there sort of pushing at the boundaries of human knowledge, or beyond everyone else, or did it feel different to that? How was it for you as inside the process?
Okay, the Nobel Prize is an institution by itself, so there is certainly some element Nobel Prize that comes from the fact it's an old prize at a time when very few scientists were doing that as a job. It was kind of a very small group, and you could identify the few people doing it. That's true that this has changed. There are big groups of scientists. That's absolutely correct, and sometimes it's really difficult to identify who deserve the most of the reward. Now, apparently the Nobel Prize still works because people still consider it as a good prize, so there is no rejection of the principle. The way they pick the people, it's very mysterious, and one of this privilege of the Academy of Science. But what I know, from the very few things I know, there is hundreds of proposals every year. And the committee is very careful at reassessing following candidate for years before they give the prize. So that's why it takes so much time. There is all these debates is in this first if the discovery deserve it, and then even if you deserve it, is who are the most relevant person that are behind it. And I say the most relevant person. It doesn't mean this is all the relevant person. It's the most relevant person, and sometimes they just wait to have the right number, which means they write the natural biology to prevail and some people to die, to have just a number which is fitting what they can do. So I understand there is a little bit of a trick here, and in a way, in some of the prize, you could debate whether it would be the best person. In most of the prize, when I know the inside story, it's not far from being obviously the right number of person. And sometimes there are a little bit of ambiguity, and you can say, well, it could have been that person instead of that one. But look, at the end, it doesn't matter. I tell you why. Well, for personal matter, it may matter to get a Nobel Prize or not. It all depends what you do with it. I used to say when they get a Nobel Prize, there's different attitudes. Most of the people, it doesn't really matter very much. You just add something on the CV, and there is a long list now in the history that not sure everybody will be remembered. So do you remember all Nobel Prize? You remember some of them, Einstein, people like that. But there'll be one Nobel Prize, these people, and nobody will challenge what they have done. So most of the other Nobel Prize, you don't really remember. In the public. So the element of the Nobel Prize is not who got the prize, it's because you talk about science. So I tend to not care very much at the end of this debate because it's a wrong debate. Because the right debate is, when are we talking about science in the public media? And how are we talking about sciences? And Nobel Prize is a perfect way to do it. You have to identify some people. So some people are being identified as, I used to say, diplomat of sciences. So you're going to get a job when you get that, and you get entitled to talk about science. Well, some people even talk about other things because they can talk about anything they like, but at least you are entitled, and it's part of one of the jobs. So I feel that the first job when you get a Nobel Prize is to become this diplomat of sciences. Of course, because of the waiting list, sometimes you just get it too old, and you don't have the opportunity to express yourself this way as a diplomat of sciences. In my case, I was lucky enough that discovery was made when I was very young. I got a Nobel Prize at still a young age, before 60. So the question is, what I do with that is a different meaning, because in a sense, it becomes for me part of a job. Like I'm used to talk about science with some validations, because I am a recognized scientist, to explain to the people that are non-scientists. For when I talk to scientists, it doesn't make much difference. But when I talk to people that are not scientists, it is entry ticket. I can entry and talk about science. And we really need to talk about science because the society is really complicated, it's highly technological, and there is a dividing line right now that we see growing between, let's say, the average populations. It includes also the politicians, all the people by education that never had the chance to understand anything about science, or they are rejecting it. And the scientists, which are by interest, by curiosity, by pleasure, are pushing the boundary, pushing the technology, and we're surrounded by that right now. There is not anything we do in the day without using technology, and it's even more dramatic right now because we're talking about the threat of the technology. The threat, controlling the DNA is great, it cures disease, but it's also a threat. We're talking about AI. It's a wonderful tool, but it's also a potential threat, so on and so on. So the Nobel Prize is this. It identifies some scientists that could be identified as people that deserve the chance to advocate for the science. It's not enough because there's way more, and I keep telling my colleagues, you should also get in J. It's not because you don't have a Nobel Prize you cannot speak. I mean, we are all legitimate to do that, but certainly I will have more impact by the nature of the prize, and that's the way I see it. So I think it's a good idea to have the prize for individuals. Look at the Iliades and the Odyssey of Homer. The texts talk about a war where there are thousands of soldiers. If you read the text, you don't have to read it in Greek, you can read it in translation of English, it's a good one. It's a poem, and you only have 4 people. Because you don't care about the 10,000 soldiers. You only care about following the heroes, the one that going to push this. So it's exactly the same. Of course, there are the 10,000, 100,000 of scientists that make this possible. But for telling stories, it's much more easy to have a couple of heroes.
It's very interesting. And I noticed it in your Nobel Prize acceptance speech, in your first foreword, you mentioned all these staff and supporters in the lab that helped the development of this. I was wondering what you think possibly is the most under-recognised sort of role that's related to physics research, because we see the sort of chief scientist, we see these sort of spokespeople for science, but I think there's some interesting roles that possibly go under the radar, and it's nice to highlight those when we can.
Well, any opportunity, I'm using it to acknowledge all the people that play a role into the success of an experiment. And it goes down to the staff secretary, down to the chief engineer. So there's all the scale which is needed. It's a human pursuit. I mean, it's a human construction. So in a human construction, everybody has a task. Everybody does it. As a chief of team that is building equipment, my way of responding to that is, first, I do care a lot for the people working with me, so I always make sure that they are well and they have the space they need to feel well and to feel the pleasure to working for something. That is really first element. So acknowledging not only just in event but in a daily basis. So it's recognizing what they do, acknowledging, yes, this is great. So I really do a lot of that because I think this is very important to make them aware that what they do has an impact at the end, and making sure I involve as much as possible into the possible event that bring a bit of light on it. And then, of course, what is usually the way to proceed is when you have a big equipment which is put online, there is a long traditions to have everybody who contributed, and you put all the names of everybody here to make sure they acknowledge in the author list. So that's the way we do that. In addition to that, it's always good to remind everybody that the science is not a single individual game. It's an activity that goes along space and time, space with many people at different places, but also time. Because what I would be doing, I would have never done it before the work of the people before me, and this not before the people ever did. And I'm not the first one saying that. Newton is starting his book by saying, I'm sitting on the shoulder of giant, and the giant that he's talking about is Kepler, for example.
Lovely. So since then, your work seems to have focused on setting up and developing multidisciplinary groups looking at exoplanets and their potential to harbour life. Now, the search for extraterrestrials can sound a little bit more like science fiction than sort of an active area of research. So could you speak a little bit about what work these groups are doing, what the sort of search for extraterrestrial life looks like in modern science?
Well, thank you for the question. So I would agree. There is a little bit of a sci-fi touch into that. Like, you had a sci-fi touch about talking about planets. So right now I'm talking about planet. This is obvious. So you even challenge the sci-fi movie by telling, oh, by the way, the planet that the astronomers are finding are much more funny than the one you guys have imagined. So you see, you have to be careful. I mean, sci-fi becomes very much boring facts at some point. That's true that life is another topic. Life has been, it's there already since a long time, the origin of life. It's very ancient. It's certainly one of the first motivation for the first biblical stories. Why are you there? We are there, and evolution. So it went into, of course, Darwin with his species, progressions, all of this. And then the breakthrough was the DNA that had been identified and how you transmit the information that came here in Cambridge. So all this created a situation where we have a good sense of what is life functionings and what is life evolution. But still, we have no clue about how all this started. We know it started a long time ago on Earth, about 3.7 billion years ago. We have evidence for that. We have traces in rocks of stromatolite, fossilized stromatolite from this time. And we know that the Earth was different at that moment. So that's one thing we know. We know that Venus is different from the Earth, but has the same mass and size. And we can ask the question, why? I mean, maybe it has been life on Venus some time ago, and maybe it's changed because the nature of the planet evolution was different. And we know Mars likely may have life as well. The only thing that happened in Mars is because there is no magnetic field, and Mars lost its atmosphere. So that was already there for some time. Now comes the planet. We have plenty of planets detected every day and all this. Pretty clear that there is a planet on every stars, at least, even more. You have 100 billion stars in the galaxies, you have billions of galaxies, so you can make the math you want. I think the possibility that one of these planets can host life in addition to the Earth is very high, because there's so many. So the idea is, okay, how can we make sense to that? Early on, when the first discovery came, we started to have concepts like biomarkers, habitable zones. So we tried to compare with the solar system and say, oh, that planet maybe has the right mass, maybe has the right size. And we would try doing that. And this was something I've been exposed since the beginning. And I always felt that was a little bit slim. It doesn't really provide a strong argument. It doesn't bring the right approach, and I could feel the interest because the public was really interested by that, and as scientists we tried to use that for promotion purposes, not really for more because we had nothing else to say. But I had the opportunity to join a group that was funded by Simons Foundations, which was a Simons Foundation Origin of Life initiative, a group of 24 scientists all over the world that was a mix expertise and trying to address the questions. For me, it has been a revolution in my mind. I was exposed to chemists, I was exposed to people, specialists of planets, planetology, evolution of our own planets, biology, all this. And at the beginning, the first meeting we had together, the idea was to build up a kind of a global program on that. I did not understand anything about the talking, and I was completely lost. I think the dividing line was huge, and we all realized we have to try to kind of teach each other in a way we at least understand what each other are doing and how far we converge, we're asking the right questions. And we have been doing that for 10 years. It has changed my complete perspective on that. I moved from the idea of a naive perspective, as everybody had, into a very practical program that it's a solvable problem, but we have to do that in the right order. And my vision now is different and is very simple, is life happened on Earth at a time when the planet was different. How far do we understand that planet? So it's a planetology problem. Already that is a good question. Do we have water? Venus maybe had never water. If you have the planet with water, what does it mean about the atmosphere? What does it mean? Do you have plate tectonics? Do you have magnetic fields? How far do you understand the early stage of the planet, our own planet? And when you talk to people doing that, they're telling you, well, not much, because everything has been erased. The plate tectonic is great because it's recycled the CO2 and all the gas, and it would just make sure you maintain some stable level, except that now because we're extracting too much CO2. But otherwise, it removed everything as well. It kind of recycled everything. So it's a very interesting program. And then for planetologists, for me, that is looking for planet under the stars, I can say, well, I have plenty of other planets. Maybe we can compare. And they say, oh, yeah, it's interesting. So already you understand that the origin of the system could be expanded and explored in a more systematic way. And we can ask ourselves, amongst all these planets that seems to be rocky than the Earth, how many have water? we may end up finding none, and water is exceptional. We may be finding plenty. So that is the kind of steady approach we can have. Then on the origin of life, the chemists have made tremendous progress. But what they need, the chemistry, they need material. They need to know what is the temperature, what is the element they have, what is the condition, what is the pH, how do you do that, how do you do that. And that depends also how many material is falling on the planet. So you understand that the input material, called the deliveries, is critical because they may stimulate or completely slow down or completely, remove life on the planet. So all this start to make a picture when you realize it's a complex problem and all the pieces has to be assembled together with some clear observations. We can play with chemistry in the lab and try to replicate origin of life in the lab. And progress is being made at this very moment in Cambridge and in different places. You can study the ancient Earth, looking at the Earth, but also looking at Mars and Venus, try to understand why exactly it was like that and what happened, and also comparing with other planets. That is being done right now. You can ask yourself, well, when you start having life, at what moment you start to impact on the planet? What is changing on the planet? What is the leftover? What is the trace of life? We all know the carbon-14, which is one of the transformation of life. So life is, there is many isotopes of carbons. Life loves carbon-14. So there is the ratio of carbon-14 is different because it has been processed by life. When the life dies, then carbon-14 is fixed forever, and then you can study the ratio of carbon-14. So that's one way to do in a general way, looking at isotopes, do you find imbalance into the isotopes, which is related to the processing of life on the planet. And what life produce in terms of gas, what you have as visible, that's looking at life on other planet remotely without going there. If you bring a piece of rock, what should you be looking at? And so on and so on. So you can come up with a series of experiments, and I insist on experiments, maybe not to answer entirely the questions, but to make progress on these questions, and maybe to rephrase the question, to reframe it in a more specific way. And I do believe that within all of this, combining lab experiment, simulation experiment, explorations of the planet and also the satellite of giant planet in a solar system, observations of other planets, getting the fact whether there is atmosphere, not atmosphere, water, no water, we're going to build up a picture with full of gaps, but this picture may help us to find out whether it's very likely that life appears on another planet. Whether the life develop long enough to reach our level, that's another story.
So you spoke about sort of the advantage of a multidisciplinary group, about how chemists and plant scientists brought different elements in and how that's helping you chip down what could seem to be an insurmountable problem. I noticed on your page that one of the groups is the Centre of Theological Inquiry in Princeton, and there's not many theologians in the physics department as far as I'm aware, at least not in an official capacity. And so I was curious as to how they contributed towards it or what their role was within these larger groups.
Well, Cambridge is a bit of a special place, so we decided when we put the proposal, the Leverhulme proposal, we had to consider the social aspect of the problem. It was a bit of a bet because it's clearly beyond my comfort zone. I mean, I understand social elements or theological element as a layman, but I don't have really this level of a scholar level here to talk about. But we got lucky at that time to have enough interest here in Cambridge to consider that the topic was worth to be considered and added to the proposal, with the idea that there is, let's say, biases or preconceptions about life that would be interested to look in the traditions. They call that the traditions. So there's different traditions, different element that is there. There's also a more philosophical aspect that people approach that, about the concept of life, how do you understand that? And it's also another element, which is also in terms of history of science, how much the biases, the preconception is going to affect your problem. You know, the challenge of this question of life is tremendous because it's, in a way, it's a kind of a singularity. We have only life as we know it. It's only one case. There is no two. There's only one. I mean, if you study a tree, you will find the same basic functioning that us. So all life on planet Earth is a single case, essentially, which is keep reproducing and evolving. It has been doing that in the last 3.5 billion years. So we have a single point, anyway, single data point, and we want to extrapolate that in a general way. So it's an interesting concept already to how do we deal with that, what are the misconceptions. So we started with this without really knowing what we would do. We had Andrew Davison here, don't know, he's moved to Oxford. He was in contact with Princeton, the group in Princeton. The group in Princeton is very famous because they did a couple of programs for NASA when NASA was exploring the concept of life and what does it mean discovering life. Princeton was involved into that and tried to embrace that through the different traditions to see how they would react to it. My personal experience is I gave a talk in a country that was from Islam traditions, and I was expecting, by preconceptions, bias, I was expecting this tradition to be a bit critical of this reading of life on another planet, and it was just the opposite. They were telling me, "Oh, no, not at all. In the tradition, Islamic traditions, there is clearly an expectation to have life everywhere, because Allah is very generous and life would be everywhere. There's no reason there would be only on Earth." And I was kind of puzzled because it's completely opposite of my few interaction I had at that time with the more Christians and Catholic tradition. No, things have changed because the Vatican is interested by the question. So I'm a member of the Vatican scholastic scientific group, and this is one of the topics they are interested also in terms of survival and species, civilization, so aspects. So there is a lot of amazing questions you can ask, and then you can even project yourself about the future for species. If you assume that there are a potential lot of planets that can bear life, because you see it, you bring the evidence for that. You can even bring the evidence there is life elsewhere. Then we come the very critical question: how come we don't see plenty of civilization around? That's a famous Fermi paradox, and we may have to conclude that it means the time life is counted. So it means because at a time you have the power to understand the universe, you have the power also to self-destroy yourself, and there is plenty enough thermonuclear weapon to wipe out our civilization. So it's a serious possibility that if we find that Earth is not unique, there is plenty of planets like that with life. My direct conclusion as a scientist would be, it means if we don't get rid of all of that, we're doomed, because that would be the conclusion that you have to draw. Otherwise, we would have seen them, or maybe they are looking at us. I don't know.
Sitting very quietly, just in case. That's fascinating. So I often find myself speaking to enthusiastic young people who are keen to get into astrophysics research but don't really have much concept of what the field consists of. I think they're more aware of sort of nice pictures from NASA and all that sort of thing. So what advice would you give to someone who's hoping to pursue a career in this area, who's looking to one day become an astrophysicist?
Well, I think first, if you have a dream, go for it, because if you don't try it when you're young, it's very sad. Sorry. So if you have the chance to do it, because you have to be at the right place and the right moment and the right education, because it's not the case for most of the people. But if you are part of this, if you have a gift, you are easy at school, you're willing to continue education process, and you want to do astrophysics, just go for it, because it will be such a pleasure for you. It doesn't matter what you will be doing next. Anyway, most of the people studying science, they are not turning a scientist. And for good reason. I think you make certainly a better living if you're not a scientist, practically, because it's just more job, more opportunities, you well pay. It's well known that scientist is not certainly the best way to feed a family. There must be other reasons for why you become a scientist, but you don't have to become a scientist. I think what matters here is to be educated as a scientist, because once you're educated as a scientist, you always will be a scientist in your life, in the way you approach life. And the curiosity you will express will keep being the same. Most of my readings of new knowledge I learn is not about astrophysics. I have such a wide interest. I love history, so I'm reading a lot about history. I love to understand what's going on, so I read a lot about the political situation, so I have to understand things. And I have plenty of other interest. I think social sciences is fascinating sometimes to understand how the behavior of the people, and there are great news, great discovery, new things being being done everywhere. I love nature. So there's so much actually. So if you have one passion, do it, and you will find another one, and so on, another one. But it's a great education. If you want to come in Cambridge, and Cambridge is just a paradise. It's a great place to study. It would be tough. It would be intense, but what else? I mean, if you do something you like, if you don't do that 100%, do something else.
Thank you. And I'm sure the Cambridge PR office will be very pleased to hear a Nobel Prize winner say that Cambridge is a paradise. And so just to wrap us up, what's the future hold for you? What have you got lined up?
Well, what's next? It's a very good question because I have most of my life behind me than in front of me in terms of time ticking. So what I'm trying to focus my time is on 3 topics. One of them, I'm a bit obsessed about detecting an Earth-like planet. That's the reason why I'm setting up here with other people, other partners in UK, an experiment called Terra Experiment. It's a new system and a new telescope in La Palma. So the new system is designed to do what everything has failed before, which is being able to observe very intensively a very few stars to detect a very tiny star like the planet Earth. So that's really what it is. We want to demonstrate it works. It's a challenge in terms of data analysis, in terms of operations. So it's a program I started almost 10 years ago. And now we have the first light a couple of weeks ago. We have the first commissioning light in 2 weeks. And we have the first scientific commissioning in a month about. So this is going on. That's one of my pet projects. And I want to push that also, possibly developing a kind of a way to multiply that kind of systems and offer a kind of blueprints for the next generation, how they can continue developing that. Because we need to explore about 1,000 stars around, and we need more than one of these systems. That's one of my pet projects. The second one is this question of life in the universe. I think I understand what needs to be done. Of course, I will not have the time, and I don't have all the knowledge needed to solve it, but I have enough energy to at least start the program and hopefully to motivate enough people to continue the program. And that's what we started the Leverhulme program here. We have a lot of people younger than me now in the program, a lot of younger professors that are engaging in this program. That's great. I hope that we are going to change a bit some directions of research. People will embrace this topic, understanding how much they are interesting, how much there are discoveries to be made, and more, not only focus on that, but on other aspects. And I hope that this is going to build a legacy. I did the same in ETH Zurich when I also have a half job. That was the main reason why I wanted to share my time, because I wanted to translate the successful stories that I did in Cambridge in Switzerland, and we just managed to do it. We are starting a similar big center right now at the Swiss side, similar to the one we have done here in Cambridge, and I hope to also, again, to stimulate a new generation. So my role is really to inspire, certainly here, and to help putting that together and use my skill of making projects and making operation to also push this program and preparing. It means also having future lectures, having fundings, advocating for strategic developments, white papers, and so on. That's my second topic. And the third one is related to my Nobel Prize. It's my diplomatic hat. I think we need to talk about science everywhere. We are facing a big challenging time with a dividing society. Even more, with even more challenge like AI coming, we need to talk about science with everybody. We need to explain what science needs, what we should do. And right now we're experiencing a very difficult period in UK with a lot of cut, especially in astrophysics and particle physics. It's quite dramatic. I don't think people have really completely understood the consequences of this cut. So I think there is really a disconnection here between the scale of the people taking decisions and the diversity of the impact of what is science in a more global scale. So I think this is one of my tasks, and I do that by engaging as much as I can, by responding to your invitation for interview, visiting places, talking also to politicians when I can, talking to a business maker. They are certainly more easy to approach than politicians and willing to learn because they can sense that this will have an impact on the business. The politicians usually, they only care about being elected. So most of them, they don't really understand really what is behind there. Some do. I had very good discussion with some politicians that they really understand the challenges, but they're not really a majority right now. And science tends to be treated a bit as a side project, while actually it's everywhere in the society. I'm not only talking about hard sciences. It's anything which is called knowledge base. We are facing a society where the knowledge base is challenged by the perceptions, what called common sense. There's something that is very dangerous. Common sense is dangerous. I think there's nothing more wrong than common sense. Knowledge base you cannot debate. They are facts. You can argue on what you do with this fact for sure, but facts is a fact. It's still a fact. And I think we may need to come back on the baseline here and to reassess what is a fact and what is just an opinion. And in the states of the easy communications and social media, all of this, I think we really need more and more. So that's why I spend a significant of my time. And when I said that, I really decided to allocate time in my diary for that, which means I have stopped other very exciting project I was doing science, because I think my legacy my impact will be more important if I try to work on that aspect than just adding a couple of more dozen of paper to my publication list.
Well, thank you very much. And you'll certainly have no disagreement here that some more scientists in politics and a bit more scientific understanding across society would be a very good thing. So thank you again very much for talking to us today. Thank you to Didier Queloz for joining us today. As always, if you'd like to learn more about what we discussed in this episode and more generally about our work here at the Cavendish Laboratory, please have a look at the show notes or go to our website. If you have any questions you would like to ask our physicists, head to social media and tag us with the hashtag #PeopleDoingPhysics. As ever, we are indebted to Chris Brock for recording and editing this episode. Thank you for listening to People Doing Physics. We'll be back soon. Until then, take care.